Hi guys, it's Rich. I am going to talk about computed radiography and direct digital radiography. This is from the content specs, section 2A, section 4. I believe that Christy is either recorded or is doing live lecture on 1, 2, 3, and 5. So my portion of this particular section for 2A is section 4. A separate video, I'm going to talk about sections B, 2B from 1 through 6, but that will be on another recording. So this is CR and DR from page 7 of the content specs, and we're going to talk about the components of digital imaging and a bit about the processing for those individual paradigms. For both of them, for CR and for DR, it consists of 4 steps. The first step is image acquisition. That's actually making our exposure and obtaining the electronic image. In the case of CR, we're using photostimulable phosphor plates, individual cassettes, if you will. For the purposes of DR, we are using the thin film transistor, and typically that may or may not be a cassette, but the processing for CR and DR is much different. And that's the second part of it, the way we process that electronic image in order to obtain the data that we have captured representative of the X-ray image and the anatomy, and how we can make it visible. Third portion is displaying that image, and as you know, X-ray film no longer exists, so this is all done now electronically, which is really valuable for us to archive the image, to save it, so that we can pull it up on demand. Also, image archiving comes with it a much more reasonable, much more robust way that we can obtain the images much more quickly and efficiently and not lose them, which was not the case in the film screen model. So at some point we're going to talk about all 4 of these. However, today, in this particular video, I'm going to limit my discussion to image acquisition and image processing of the CR and the DR model. So I think that you're all aware that image acquisition is the process that distinguishes the computed radiography from direct digital radiography. The cassette-based system is CR, and the cassette-less system is DR. This is to say that with CR plates, we would actually take a cassette, much like a film screen cassette, in size, and we would take that perhaps to the operating room, perhaps to the intensive care unit, perhaps using it in our department in our existing Bucky. With DR, we use an image receptor, but it's not necessarily like a cassette itself. I'm looking at this flow chart here, and we're looking at CR, which uses barium fluorohalide as the photostimulable phosphor. That's the elemental constituents in the phosphor plate to capture the latent image. Moving over to indirect DR, there are 2 paradigms, including cesium iodine and gadolinium oxysulfite. And then the other one for indirect is cesium iodide, which is not coupled to a thin film transistor, but it's coupled to a charge couple device. And then finally, if my picture is overlying amorphous selenium in the direct DR system. So let's talk about all of those in a little bit more detail, shall we? And we're going to start with computed radiography. These systems use an imaging plate in a cassette instead of a piece of film in a film cassette. So it is a cassette, but inside is not a piece of film. It's a matrix. It is a plate that's made up of a photostimulable phosphor. It's a phosphor material that is activated by light. And in fact, that sounds like something that we saw in the film screen era. And to some extent, it's true. There are some parallels, but there are also some significant differences. And this photostimulable phosphor absorbs the X-ray photons exiting the patient. Some of them will interact with the phosphor and become light, and some of them will just be absorbed as electrons, and based on a chemical process, based on an ionization process, those will be captured, and that becomes our latent image. So the elemental constituent is barium fluorohalide, and that's what is used in the photostimulable phosphor plate. Now, I will talk about some individual of these chemicals. What you can be aware of is that each chemical is specific to its own system. It's not that we're not going to use barium fluorohalide in any other area except in CR for the photostimulable phosphor plate. And that's going to be true with amorphous selenium and gadolinium and on and on and on. All right, moving on. So these individual plates, these photostimulable phosphor plates, they are composed of several different layers. The protective layer, which does just that. It protects the phosphor layer and all of the subsequent layers underneath it, because these are all important at some point in the process. And so we can talk about all of these individual layers to some extent. And let's start at the back. That backing layer is about 1 millimeter thick, and it may be flexible or it may be rigid. It protects against damage during handling. This is not to say the handling of we technologists putting the image receptor into the table bucky or behind the patient in the intensive care unit, but the processing of the CR plates is such that the image plate is going to be taken out of the cassette and it's going to be run mechanically through an image plate reader. And so this backing layer, protects against damage during that process. It also, the backing layer has on the outside of it a barcode label to identify the image plate and match it to a particular cassette. Okay, and so the intent is that when we're using CR, we're going to identify our patient from the modality work list, and then we are going to identify the cassette that we used for this particular projection, and then additionally, from another video, we're going to identify the lookup table or how we want that individual cassette to be processed so that it looks like a lateral chest as opposed to a PA chest, as opposed to an oblique hand, as opposed to a scapular Y shoulder. So all of that is on that backing layer, and an important aspect of this is the barcode label to identify the image plate. Okay, coming internally then, we have the light shielding layer, and that prevents light from erasing the data on the image plate or from leaking through the backing. We want to, when we make an exposure, we want to preserve all of that light and all of those interactions, and we want them to remain within the confines of the image plate. So from that perspective, we have a light shielding layer. We have a support layer made of polyethylene terephthalate. It's made of plastic. How about that? And it gives support to that photostimulable phosphor plate. We have a conductor layer, and that grounds the plate to eliminate electrostatic problems. Yes, we want some light to happen, but we don't particularly want some static electricity to happen within there, because that is going to create, as you know, an artifact. I don't know if Christy talked about lightning artifacts that we used to get with film screen when the humidity was too low, and when you rub the individual pieces of film together in an environment that's too dry, it creates static electricity. Well, static electricity will expose a piece of X-ray film, and so we would get these lightning bolts across it. Well, it's the same idea with that conductor layer. So the conductor layer grounds the plate, and it also absorbs light to increase sharpness. Essentially the same idea as a grid will absorb scatter to increase sharpness. That's a pretty good analogy for it. Coming up closer to the top, we have the phosphor layer. This is where the magic happens. This is also known as the active layer. This holds the photostimulable phosphor plate, which is the active component of the plate. And this photostimulable phosphor is largely europium-activated barium fluorohalide crystals. And there is some variability to that, but by and large, these are the terms that you're going to hear: europium-activated or europium-doped, if you will. And these are halides. They are 85% bromide and about 15% iodide. Okay, and so that is the emulsion, if you will, or more specifically, that's the photostimulable phosphor that we use as the active portion of obtaining an image in the CR paradigm. And then finally, we talked about the protective layer, thin, clear layer of fluorinated polymer, again, plastic, shields the phosphor layer from mechanical wear and cleaning solutions. Remember, I said that the image plate is going to be put into an image plate reader, and it will be mechanically driven through the image plate reader and scanned. And so we want to protect it from any of the whirring mechanisms and, any kind of friction that might befall it as it does that journey. So it has a smooth surface, and that provides a better signal-to-noise ratio. Remember, a signal-to-noise ratio is important. We're interested in signal, and we're not interested in noise. So we want to minimize noise wherever we can at the benefit of increasing signal. All right, so how does it work? What happens? Well, we make our exposure through the patient, and the exit radiation strikes the image plate. That's what we call these, our image plates. The X-ray energy is photoelectrically absorbed by the phosphor crystals in that photostimulable phosphor plate. And some of the absorbed energy is converted to light based on the fact that it interacts with phosphor. However, that light, while it does momentarily exist, when the exposure is terminated, that light goes away. We do not capture it at all. However, some of the energy is retained in the phosphors, and that is the portion that constitutes the latent image. And so, yes, there is some light that is produced, but we don't capture that light. In the film screen industry, we did capture that light, but in the photostimulable phosphor, we do not. So some of the energy retained in the phosphor itself is what is in there now, is the latent image. And then it's a question of processing that latent image so that we can make it into a manifest image. Visible light is formed when some of the crystals in the plate are ionized, which is photoelectric, and producing electron hole pairs within them. Okay, this is kind of a challenge to wrap your brain around. Then electron hole pair raises the europium to an excited state by liberating one of its electrons and changing it to europium-3, which quickly returns to its ground state, giving off some visible light. Okay, and that visible light then, that is, I won't say wasted, but it's it's no longer a factor. However, the remaining X-ray energy is absorbed, and the ionizing event causes the crystal electrons to be trapped in the empty sites, and those are called the F centers. I don't know what F in this case refers to, but the book refers to it as an F center. Because the electron energy is trapped, the image plate is called a storage phosphor plate. So the photostimulable phosphor plate is a storage place for the latent image. And these then are the latent image that will be used to create the digital image for the computer to process and then to display. And so we will talk about that. Important to remember with CR plates that the latent image will remain stored for about 24 hours, but will gradually weaken through a process called fading. And fading occurs exponentially over time through spontaneous phosphorescence. Essentially, we start to lose the intensity of the signal. Okay? And it is therefore important that we process a CR plate as soon as possible after exposure. Here's the reason why. A typical plate loses approximately 25% of its stored energy within 8 hours after exposure. Okay, 25% within 8 hours. Okay, so let's look at an example here. I'm going to Babyland to take a chest X-ray on a newborn. Okay, and perhaps that newborn is premature, and so only weighs 1 or 2 pounds. So I'm going to use a very, very small technique, perhaps only 0.6 mass. If that image plate remains unprocessed for 8 hours, my 0.6 mass, well, it would be like I took that X-ray image at 0.45 mass. Or, if I leave it until the next shift, it would lose half of its energy over 14 or 16 hours. And you can see that that's not a tremendous amount. What happens if we don't have enough MAS to expose the plate? You remember quantum model is directly related to the amount of MAS. So from this perspective, you can see that it's particularly important to process our CR plates as soon as possible. Reading the latent image. After being exposed, the CR cassette is inserted into the CR reader. Those are those great big machines. Sometimes you can only put 1 image plate in. Sometimes you can put 4 or 5 image plates in. Okay, and there's an example of one type of image plate reader on the bottom of this illustration. The CR reader takes my image plate and automatically opens it and takes the image plate out. CR readers are able to process 30 to 200 plates an hour, depending on the model. In my experience, it's about 1 minute per plate of processing time. Some tables and upright Bucky units contain multiple photostimulable phosphor plates and an internal reader, so no cassette handling is required. And this is a Fuji product. I'm not familiar with that particular product, but I can see how it could be put together, especially if you have like a dedicated chest X-ray room, for instance. In any event, taking a look at this top illustration, we have an individual plate, and we're able to put that plate in. It opens the plate and scans it, and then it goes through a process of reading it, scanning it, erasing it, and getting it ready for reuse, and then it returns it to us. So we're going to talk about those individual steps as we go through. And so let's start with that now. The image plate is fed through the transport rollers to the scan read section. So now what we're looking at is that blue plate. That is the imaging plate itself, and it's been taken out of the cassette, and it is moving through the rollers. So it's the plate itself that moves. And so this is why we have the protective layer and the backing layer and the support layer, so that it gives it enough structural integrity to withstand that trip through the image plate reader. Okay, the image plate is scanned with a laser light, and that reads the latent image from the phosphor layer, and this is called readout. So I'm looking at this illustration, and I see the phosphor plate, and the phosphor plate moves slowly in that direction along its long axis. Okay, there is a scanning laser. Can you see it up above? And that scanning laser, a laser is light, and light can be focused, so that light is focused and focused onto a mirror so that it projects onto the plate as the plate is moving. Okay, and the action of scanning that individual plate with laser light allows those trapped electrons to be liberated. And as they are liberated, they give off their energy as visible light. And that visible light is captured in a photomultiplier tube. Okay, so let's not go any further yet. So here comes my image plate subjected to the laser light. And you can see that the image plate is moving continuously in one direction. So we're scanning the plate from end to end sequentially and in order, so that we can keep track of how much light is given off at what area of the plate. And this is important when we process the image and then we display it. The red helium neon laser at about 633 nanometers, or solid state lasers at 670 to 690 nanometers are used. And remember the F centers? Well, these F centers respond best to red light having these wavelengths. So what's important here is that the laser itself is red. It is a red laser light. All right, moving on. So the plate is scanned by the laser beam in a transverse raster pattern as it passes through the reader. Now, notice that the image plate is moving along its long axis, but the laser beam is scanning it across its short axis. And so what we call that is the movement of the plate along its long axis. That's called the slow scan. And the laser beam scanning it across its transverse axis, that is known as the fast scan. Will that be on the National Board Certifying Exam? I don't know. But it's not too difficult to wrap your brain around, so it might be a good idea to hang on to it. Okay? As this laser beam releases the light, that light is captured by a photomultiplier tube, and that light intensity is representative of how much exposure that particular area of the plate got. Okay, so it may vary from a little bit of light to a lot of light, and that is captured in the photomultiplier tube as an analog signal. That analog signal then is going through an analog to digital converter, and that's what takes those individual analog values and digitizes them, assigns them a discrete digital number. And that stream of data is what becomes the values that we need to process the digital image. As the laser beam passes over the image plate, the trapped energy, or the latent image, is released in the form of visible light. and that light is emitted from the IP by the laser light stimulation, and that's a blue-purple light with wavelengths of 390 to 400 nanometers. Okay, and this is the process called photostimulated luminescence. Okay, it's no longer captured. We have now released the latent image. And so we are, by the process of exposing it to the laser light, we have luminescence. Now, the intensity of the photostimulable luminescence is directly proportional to the amount of X-ray energy absorbed in each area of the phosphor. So as I say, if there's a little bit of exposure, there's probably a little bit of signal. If there's a lot of exposure, there's correspondingly more signal. And so from that perspective, this is how we can accurately read how much exposure is in each individual area on the plate. The drive mechanism moves the image plate slowly along its long axis, and that's the slow scan. A deflection device, a mirror, deflects the laser beam back and forth across the image plate, and that is the fast scan. Important that the drive mechanism and the laser beam are coupled so that the beam is blanked during the retrace of the scan pattern. As it goes back to 0 to scan the plate again, it needs to be representative. It needs to understand that we have already scanned that line, and so we need to move the plate forward incrementally and scan the next line. The error tolerance for this mechanism is in fractions of a pixel. And so you can imagine that it is adjusted very carefully and very closely. If we have image edges from a reader that's out of tolerance, then they may appear wavy, and we understand that that is a drive mechanism artifact, and a clinical engineer would be required to adjust it. So here's an illustration of it from, I think, from a different textbook. What we have on the top here is the laser, and the laser coming through an intensity control. I'm not real clear what the intensity control is or whether they all have them, going through some beam shaping optics. And you can see that there's an oscillating mirror, and the oscillating mirror moves back and forth sort of, where am I here? Sort of like this, so that the laser beam on the edges is just as clear and geometrically stable as it is on the edges. I think that when we did imaging and technique, I gave you guys an example of a flashlight right at you, and so that shows up as a round circle. But if I turn it off this way, it becomes oval. If I turn it off this way, it becomes also an oval. So in the center, in order to keep it in the center, we have these beam shaping optics, which, despite the fact that we're scanning the periphery or right in the center, we get the same signal geometrically with all of the values that it ought to, as opposed to having it distorted. Optical features deflected across the IP, it would change the size and shape without the beam shaping optics, which is what I just talked about. These keep constant laser beam size, a constant shape, a constant speed, and intensity. The laser beam size must be small to ensure high spatial resolution. It's kind of like the line focus principle. Having a very small area to start with will give us the best spatial resolution, as opposed to a larger area. There's some inherent distortion, there's some inherent unsharpness that is built into that. The photostimulable luminescence is collected by an optical collection system called a light channeling guide, and that consists of the light gate and the light collection optics. You can see them. The light collection optics is there, the light beam of the blue-purple resultant light coming off of the image plate. The channels This channels the light through optical filters to one or more photomultiplier tubes, and these are the tubes that convert the light energy into electrical energy. Okay? And then the electrical energy is a time-varying analog signal. It's not digital yet. It's an analog signal that's processed for amplitude, for scale, and for compression. And this is all a part of the processing having to do with not yet the lookup table, but we're looking at the signal, and the equipment is making some manipulations to it in order to have the best spatial resolution that we possibly can get. This shapes the signal before the final image is formed. Now, something that I found in Bouchon, and this is not in the slide series that you have posted, but I thought that it was important that you have an understanding of this. Increasing the sampling frequency increases the pixel density and improves the spatial resolution. Increasing the sampling frequency increases the pixel density and improves the spatial resolution. Here's why. The more the signal is sampled, the more information is obtained, and the smaller the pixels can be. With smaller dimensional CR plates, the sampling frequency is higher and therefore yields improved spatial resolution. I think that I have been saying right from the beginning that we want to use the smallest CR plate as we possibly can. Okay, this is why we don't take x-rays of newborn infants on a 14 by 17 CR plate. Now, this is not necessarily true in the direct digital environment, because in the direct digital environment, it's not obtained quite the same way. But in the CR environment, if we have an X-ray image of, for instance, lateral nasal bones or a wrist or a finger, we're going to use a 8 by 10 image receptor, or the smallest image receptor that we possibly can, to get better spatial resolution. Okay, so this is sampling frequency in CR, which is a bit different than where it is in the DR environment. And we'll talk about the DR environment a little bit later. Moving on. The electrical energy is then sent to an analog to digital converter, the ADC. All CR systems sample the incoming analog signal at discrete points. And you remember Nyquist? The requirement is that the signal be sampled twice, at least twice, from each cycle. And that is the Nyquist frequency, or the Nyquist theorem. If we don't scan it according to the Nyquist theorem, then chances are that we are going to get artifacts, and or we are going to get an image that is not representative of the anatomy that we try to image. So it needs to be at least Nyquist, twice from each signal. The analog to digital converter, that's the electrical energy is digitized into binary code. This is where we finally take that analog signal and it's digitized with respect to the position. Remember, we did the slow scan so that the computer knows exactly not only the intensity of the light in that particular area, but also where it is on the plate. So we have the spatial location and by intensity quantization, which is the value of each sample or gray level. And then based on the fact that we know at what area is what value, the computer can then process this digital signal and give us a resultant image. The last step in the reading process is that after the image is sent to the computer, the plate is exposed to an intense light which removes all vestiges of the latent image. This is image erasure. And I think that you remember from RadTech Boot Camp, incomplete erasure causes ghost images. Okay, and so if we see ghost images, if we see that lateral skull that shows up just as a shadow on some of our subsequent radiographs, well, then we may consider that we have some ghost images going on there. Recognize that photostimulable phosphor plates have a lifespan of about 10,000 readings. We can reuse them thousands and thousands of times. It's from this perspective that this equipment, although it is somewhat outdated, it is still very expensive, and we need to respect the investment that our employer has put forth to have this equipment available for us. So here is exposure, where the remnant beam comes through the patient, comes through the bucky, and interacts with the photostimulable phosphor plate, where we have some emission of light, which is lost, and we have those F centers, which are then become the latent image. Taking that plate, then putting it into the image plate reader, it is subject to a stimulating laser. That stimulating laser scans the individual surface line by line in a sequential pattern. The action of the laser beam releases blue-purple light, and that is visible light, which is captured in the photomultiplier tube and then sent to the analog to digital converter. And then finally, before we return the plate, we will expose it to intense light. I'm told that this is a fluorescent light, but I cannot say that with certainty. And that erases the plate and gets it ready for reuse up to 10,000 times. For further information on the CR process, you can refer to Bouchon chapter 15 and Carleton chapter 21, which is the reference material that I used largely for this presentation. It's now 2 days later, went by in the blink of an eye, didn't it? And I am going to continue and talk now about the direct digital radiography, cassetteless DR, which is a largely different process for processing the image, but there are some similarities between DR and CR. So let's talk about DR, which the image receptors have a self-scanning readout mechanism that receive the exit radiation and convert the X-rays into electronic signals for digitization. The large difference here is that with DR cassettes, or what we call thin film transistors, flat panels, have a variety of different names, it is a process that happens very quickly and at the same time, as opposed to in the CR system, taking the image receptor and putting it separately into an image plate reader for processing. CR requires this two-step image acquisition process, and there's a delay between the image capture and the image readout. And that delay, as we said, is on the order of 1 minute processing time per image receptor. With DR, the imaging combines the two processes of obtaining the image and then displaying the image, processing it, and displaying the resultant image almost instantly after exposure. And I think that you all have some experience with DR. Those images come up in 3 or 4 or 5 seconds. Often those images will come up on your screen before the collimator light has even turned off. So briefly, with the DR system, what happens is the X-rays come through the patient, come through the bucky, come potentially through the grid, and are interface with the thin film transistor plate or the flat panel plate, and they are in the direct conversion. The X-rays are immediately turned into an electrical charge, and the mechanism is fueled by something that we call amorphous selenium, ASE. SE, amorphous selenium, and that is the system that immediately turns it into an electric charge. That electric charge then is stored in the storage capacitor, which is a part of the individual pixels on the flat panel detector. And the thin film transistor, that is the part of the process where the data is uploaded to the computer in a sequential pattern. So we know how much exposure, which has been quantified and turned into a turned in by an analog to digital computer, converter, all a part of this process. All of that is done immediately, and then we get a value from a certain pixel at a certain place on the plate, and that value is recorded, and also the address of where that value was is also recorded. So in a nutshell, that's DR. The flat panel detectors, they're constructed with layers, just like a CR plate is layers, but these are different layers in order to receive the photons and convert them to electric charges for storage and then for readout. So it's all put together as one process. The first layer is composed of an X-ray converter, and that X-ray converter reads the X-ray, senses it, and doesn't turn it into light. There is no light associated with direct digital radiography. There is light associated with indirect, and we're going to get to that in a minute. So the first layer is composed of an X-ray converter, and that immediately turns it into an electric, not signal, but it recognizes how much charge has been there, how much exposure has been there, and quantifies that as a number. The second layer houses the thin film transistor array, and that's divided into square detector elements, DELs. I think I've talked about that. Each having a capacitor to store the electric charge and a switching transistor, the thin film transistor, for readout. The electrical chargers are separately read out from each detector element. So all of these pixels have its own thin film transistor and capacitor. So then that electronic signal is sent to the ADC, which is also associated with the thin film, with the flat panel detector, and that's sent for digitization. The final layer of this panel is a glass substrate layer to give it rigidity and, a structural framework. So what I have here is an illustration, and I don't know which textbook this illustration comes from. The copyright on it, as I'm seeing, is relatively old. I'm not recognizing this from Bouchon nor from Carleton, but nonetheless, the direct acquisition system directly converts incoming X-ray photon to an electronic digital signal. That paragraph, that sentence right there, sums up digital direct imaging. The exit radiation interacts with the detector in the flat panel direct capture detector, or with a charge coupled device. A charge coupled device, now that is, when we're using CCDs, we're talking about light. Because up to this point, I've been discussing direct digital or direct conversion. With direct conversion, there is no light made. Their light is not a part of the process. However, with indirect conversion, light is a part of the process. And one of the terms here is charge coupled device, CCD. You have a charge coupled device in your phone as a part of your camera function. Or if you have a digital camera, dedicated digital camera, that has a charge coupled device in it. Okay, Charge coupled device is a light device that is able to see light and represent the individual values for display. So think about how an X-ray image is similar to taking a picture and displaying that picture. And the value with charge coupled devices is that it happens very quickly. When you take a picture on your phone, how long does it take to process it? How long does it take for you to be able to see it? And the answer is about the same amount of time as it takes for a direct digital radiography image, either direct or indirect, to come up and be displayed. And so I think that using CCD technology in radiography is a spin-off from that whole industry. Currently, 3 types of detectors. They differ in how the X-ray energy is converted to an electric charge and how the system is captured before it's sent to the computer for processing. So we have, I'm looking at this illustration now, and where's my mouse? Here we go. So this one is the film screen model. I have X-rays coming through the intensifying screen. The intensifying screen has phosphors in it. The X-rays cause the phosphors to fluoresce. The fluorescent light exposes the film. Okay, and in this case, I have intensifying screens on both sides of the film. We call that double emulsion film. And so I can use X-ray to expose the film, and then processing the film. That's how I get my resultant image. The next one over is the charge coupled device. A charge coupled device uses a scintillator. The indirect process uses light. And whenever there is light associated, there's some way that we convert that light to the capture element to be stored. And so when you see the term scintillator, that refers to the indirect conversion process, where there is light involved. Indirect, light involved. Direct, no light involved. The X-ray is immediately turned into an electronic signal. It's just immediately captured without light. And then moving on to the last part of this illustration, flat panel direct capture. Well, we have the scintillator phosphor. In indirect, we have something called cesium iodide. Cesium iodide is considered a light capturing device. So the X-rays interact with the cesium iodide, and the cesium iodide transmits that light, changes it to an electric charge, and transmits that value to the thin film transistor array. And that is where that charge, that value, is sent sequential order as a part of the data for that particular image. So flat panel direct capture, we have an indirect process and also a direct process. As I said, the far right, that is X-ray photoconductor. That's the amorphous selenium. Notice that there's no photodiode in there. It's just immediately converted to an electrical charge. With the indirect system of DR, we have a scintillator, or look at the term photodiode. You remember from medical terminology, photo means light. And so whenever you see the term scintillator, whenever you see the term photo associated with it, they're talking about the indirect system, where a photoconductor, what we have here is the immediate transfer of that value to an electrical charge. So yes, I know we're using the same term in 2 different ways, and that probably confuses the issue. Nonetheless, there is only CR is its own process. Film screen is its own process, and DR is its own process, but will have direct conversion or indirect conversion. So what do we have here? The active layer for direct digital is amorphous selenium, and that's a semiconductor, and it has really good spatial resolution. Now, it says greater than 20 line pairs per millimeter, and I think that that's wonderful, but I wonder how they were able to capture that, because we can't, it becomes very difficult for us, as you know, to display images with that level of resolution. In any event, you can see sort of a cross-sectional diagram of this flat panel detector. We have the carbon fiber base, an electrode, dielectric, and then the amorphous selenium. This is where the magic happens. The X-ray photons are converted immediately to an electric charge. That electric charge is then stored in the capacitor and read out through the thin film transistor. And you can see that each of these has its own analog to digital converter. So the number that we send to the computer as a part of the signal, well, that number, the computer then knows what to do with it. It doesn't need to process it further in order to make it usable. Prior to exposure, a high voltage charge is applied to the top surface of the selenium layer, and that makes it ready to receive photons and ready for the process to happen. Ionization caused by the exit beam absorption causes the electrons to be freed from the selenium, and then these electrons are collected at the bottom of the selenium layer, and that represents the amount of exposure that that particular pixel or detector element got. The charge is collected and then transmitted through the thin film transistor to the computer for processing. So again, each pixel has its own analog to digital converter. Charge is collected and then transmitted through the thin film transistor. I don't know if the board exam is going to ask you questions about what part or the order of steps that the process has. So be aware that the charge is temporarily stored in a capacitor. For those of you who have studied electronics, you know that a capacitor is something that can store a charge, but then the thin film transistor, that is the gateway by which we upload the signal in its turn as a part of the signal to the computer. So that is, in a nutshell, that is the direct DR amorphous selenium paradigm of direct digital radiography. The indirect is in some cases similar and in some cases extremely different. The indirect systems are a two-step process, not one step, not immediately turned into an electric charge, but in fact some light happens as an interim step. So the absorbed X-rays are converted to light, and this is called scintillation. So when we see the term scintillator or scintillation, then that is referring to the indirect process. And this light is then converted to an electric charge. So X-rays to light, and then light to an electric charge. The indirect system, incidentally, is not unlike what we talked about with the CR paradigm, where the latent image is released as light, and then that light is turned into the resultant signal, which goes through the analog to digital converter. So all of the steps are there, it's just that they happen in a slightly different way. All right, so step one. This one is not amorphous selenium, this is amorphous silicon. And amorphous silicon, this is the scintillator. Amorphous silicon, incidentally, another term for it is cesium iodide. I'm not a chemistry major, but I'm given to understand that when we refer to amorphous silicon, we're talking about the cesium iodide, which is probably more common. And another one that we used for a period of time was gadolinium oxysulfite. There are some advantages and some disadvantages to each. The cesium iodide is much more delicate and cannot withstand sort of rough abuse that a flat panel detector might encounter if it's being used constantly for quite a number of patients in a busy X-ray room. And occasionally they hit the table a little harder than you might want them to. And so the cesium iodide has gotten a lot better over the years. Gadolinium oxysulfite, it was a much more heavier duty media, but the problem with it is that it didn't have the spatial resolution as did the cesium iodide. So it's a trade-off, one for the other. In any event, when X-ray comes down, these materials, cesium iodide or gadolinium oxysulfite, emit a flash of light in relationship to the X-ray photon exposure that they received. If they got a lot of exposure, then they might produce more light. If they get a little bit of exposure, then the light is proportionately less. Then the amorphous silicon works as a photodiode, a light detector, to capture this light created on the exit X-ray absorption by the cesium iodide or the rare earth phosphor. And so essentially, it then converts the light into an electric charge. Okay, you with me so far? The charge is stored briefly in the thin film transistor until readout. And so the readout process, notice that down here, all of these are a very exploded view, but these are individual pixels. Okay, and so each one of those is holding onto a charge ready to send it, and they are downloaded line by line. Some voltage is applied, one line is sent, that voltage is released and voltage is applied to the next line, and that line of data is sent, and so it goes on and on. And consider your X-ray image comes up on your monitor in 3 or 4 seconds, and how many pixels are there? So when you think about the sophistication of this equipment, it really is quite remarkable that we're able to do this, and we're able to do it with such clarity and such resolution and so quickly. This is the state of the art in our industry today. The design of scintillators. I'm sorry that my picture is right over this this illustration, but this illustration is a part of the PowerPoint that has been posted on the website, so you are able to go and see this illustration a bit better. Or you can also see it. I think that Bouchang and Carlton do a pretty good job with their own illustrations for this. In any event, scintillators emit light isotropically. Isotropically means that they emit light sort of evenly all around, kind of like a halo. And this isotropic light emission can reduce spatial resolution because it's not right on a single point. It's sort of on a larger, rounded sort of area. Cesium iodide, however, is manufactured as structured crystals in the form of needles or columns, and they're 10 to 20 microns in diameter, which is pretty small. And so this light is then directed down these individual needles, and that significantly reduces the light spread. So as a result, the cesium iodide has much, much better spatial resolution. The downside of it, as I said, is that these individual needles are somewhat delicate, somewhat fragile. The rare earth screen detect scintillator is designed as a thin screen, and that's designed to minimize this light spread. All right, so what do we have? A comparison of amorphous selenium to amorphous silicon cesium iodide. And so direct selenium, no spreading of light. You know why? Because there is no light. So based on that, this direct selenium, direct conversion, which is the illustration here on the right side as you're looking at it, the X-rays immediately turn it into an electric signal, and that is best spatial resolution there. The amorphous selenium is an indirect process. It has pretty high detective quantum efficiency. And as you remember, DQE is a measure of how efficiently the detector is in capturing the information related to how much noise is present. So detective quantum efficiency is looking at the signal-to-noise ratio. And we want to have high signal-to-noise ratio. But we also want to do so with the least amount of exposure possible. And so if we can get an adequate exposure at a reduced dose, well, that is the goal. And so with indirect silicon, we're able to achieve that. And that is this illustration here in the center, where yes, there is some light that is produced, but that light is directed right down to be captured, perhaps with the charge couple device, the CCD, which is not unlike a little tiny TV camera. And I'm going to talk more about those in a minute or two. So increased detective quantum efficiency equals decreased patient dose. Bouchon does a pretty good job on this. Pages 299 through 301 talks about this stuff specifically. The thin film transistor. This is used to collect the electric charge from both the direct and the indirect system. So now we have a value, a number, representative of how much exposure that pixel got. And now it's a question of taking that number and sending it to the computer for additional processing. So the thin film transistors are arranged in an active matrix array. Okay, so this is the image receptor, essentially, that we're using. And it's a matrix. Remember, the term matrix is an organized number of rows and columns composed of individual detector elements. And we are able to, different manufacturers have different size matrices that are available. And that has a significant portion to do with the spatial resolution, ultimately, of our image. So each thin film transistor and its X-ray detector represents one pixel. And over here, these are individual pixels. Okay, and I have in that individual pixel, I have a storage capacitor and I have a thin film transistor. Okay, and notice that it says on the left side of that illustration, I have an address driver, and that address driver is able, I'm seeing a matrix here of 3 by 3, which is 9, and that address driver will recognize and keep track of pixel number 1, or position 1, column 1, has a certain value, and then row 1, position 2 has a different value, and 3. And so as the voltage is applied to that first line through the gate line, then that row, all of those values are sent, and then that gate line is discharged, and then we charge the next one for the next row. And so this is how we can keep track of which pixel represents how much value. Okay. Yes, on the bottom there, the charge pattern is read out on a pixel by pixel and column by column basis when the gate is activated by the computer. I think that it is Carlton who does a better job describing this process. The pixel size is the influencing factor on spatial resolution. And currently, pixel size is about 100 micrometers, or 5 line pairs per millimeter. And that's pretty good for digital radiography. As you recall, it starts at about 1.5 and goes up from there. And this chart represents that the pixel size and the spatial resolution. So when we have a large pixel size, you can see that we have a pixel size of about 200 micrometers. Then we have not as much spatial resolution as when we have a pixel size half that large, and our spatial resolution is correspondingly much better. Again, you can see this chart on the PowerPoint that is posted on the website. Fill factor. This is a term that I've run into so often that my suspicion is you may see a question about what is fill factor in relationship to digital imaging. And the fill factor has to do with the detector. I'm looking at a pixel. I'm looking at an individual pixel. And the gray portion of this pixel detector, this is the light capturing area. And so if I have a large light capture area in relationship to the storage capacitor and the thin film transistor, which are also a part of the pixel, if the detector portion represents 80% and the storage capacitor and the thin film transistor represent 20%, then I have a fill factor of 80%. The percentage of the pixel element occupied by the X-ray detector is the fill factor. And you can imagine that different manufacturers, they manufacture them a little bit differently. So the higher the fill factor, the better the detective quantum efficiency. Can you see how that works? Because I've got more area to capture the signal, and so I have less signal that I might need to give it. Pixel size versus fill factor. As the pixel size is reduced, spatial resolution increases, but the patient dose also increases. And so this makes sense from the perspective that you remember that pixel size is the final determining factor of the spatial resolution. So smaller pixels result in better spatial resolution, but smaller pixels may require additional exposure. With smaller pixels, the fill factor is reduced, but the thin film transistor and storage capacitor still occupy the same size. So X-ray intensity must increase to maintain adequate signal strength, adequate signal-to-noise ratio. Okay, so be aware of fill factor. I don't know if that's going to show up on the board exam, but my gut is telling me that you may see a question about that. I promised that I would talk about charge-coupled devices. And so CCDs are also a part of the indirect DR system. These are silicon-based semiconductors. They're little devices, okay? And they capture light, just like in your camera. The CCD, they're tiled, which means that they're put together in an array. And you can see on this cesium iodide phosphor, the illustration on top, I have a number of charge couple devices that are tethered by virtue of a fiber optic cable, fiber optic, right, transmitting light. And so this 9 by 9 matrix, this may represent, let's just say that this represents my image receptor. And so on each of those 9 individual portions, a small portion of each one of those goes down to an individual charge-coupled device. And then that charge-coupled device amalgamates all of those signal intensities and displays them as grayscale. This is not unlike, here's an analogy for you, this is not unlike the Jumbotron at the sports arena, where we have individual pictures that are put together in an orderly display so that we're able to see what's going on the field. So it's the same kind of idea there. The tiled CCDs receive light from the cesium iodide scintillator phosphor that's transmitted through the fiber optic cables, that fiber optic taper there, to the CCD array. And so these have high X-ray capture efficiency, and they have good spatial resolution, just like your digital camera in your phone has good spatial resolution. And it happens very quickly, and it represents a pretty good likeness of what the scene was that you were taking an image of. Another one that is similar to that, although I don't know that they are as prevalent in the industry, that's called the complementary metal oxide silicone. This is a specialized pixel sensor that converts X-rays to light photons and stores them in capacitors. And again, each pixel has its own amplifier, which is switched off and on by circuitry within the pixel, converting the light photons to the electric charges. And so it does the same thing, but in a slightly different way. CMOS, they're very efficient, and they have a larger fill factor than the charge-coupled device. But there are some disadvantages to CMOS, and one of them, as you remember, is that they are easier to manufacture, but the quality control of that manufacturing process is more variable, and so we may get quite a number of bad pixels with the CMOS. In any event, they are in our industry. And they serve the same function as the charge-coupled device. All right, little summary here. And incidentally, this portion of it is a few slides that I have added, which I think helps to summarize the process. So you saw this slide earlier in this presentation, where we have a capture element, and that capture element for CR was barium fluorohalide on the photostimulable phosphor. For indirect, we have cesium iodide, or we have gadolinium oxysulfite, and for direct DR, we have amorphous selenium. The coupling element, how we put the capture and the collection together, well, in CR, that's a lens and fiber optics. Remember, the lens is like the photomultiplier tube, and that captures the result, the liberated electrons, which is the blue-purple light that is emitted by the action of the red light laser. With indirect DR, we have fiber optics. With indirect DR, we may also have a contact layer. The fiber optics are from a CCD or a CMOS, or indirect may also be with the gadolinium oxysulfite. We may send it immediately to the thin film transistor. And then with direct DR, we have amorphous selenium. There is no coupling element. It's immediately it goes to the thin film transistor. So remembering that the capture element, that in which the X-ray is captured, the coupling element, which transfers the X-ray generated signal to the collection element, and the collection element itself may be a photodiode, maybe a charge-coupled device, or maybe a thin film transistor. Okay, looking at all of these individual parts of the process and how they're accomplished by the individual different types. The capture element, photostimulable phosphor for CR, cesium iodide or amorphous silicone, gadolinium oxysulfide is the other one, and the direct capture is amorphous selenium. And finally, the coupling element transfers the X-ray generated signal to the collection, and that's done indirectly by a lens, by a fiber optic assembly, or the contact layer, and directly through the amorphous selenium. We collect the electrons through a photodiode, a CCD, or a thin film transistor. So this is how this stuff works. Direct and indirect. I think that that's probably the most important thing that you can remember. All of it's important, but drop dead, this is two conversion layers, two conversion methods in thin film transistor flat panel technology is direct and indirect. Direct sensors are TFT arrays of amorphous silicone coated with amorphous selenium. Direct sensors absorb X-ray photons and convert them immediately to an electrical signal. Indirect uses a scintillator that converts X-ray to visible light, which is then converted into an electric charge that's collected by a field effect transistor or the silicone thin film transistor. So be aware of the difference between direct and indirect. So for further information on this stuff, take a look in Bushong, chapter 16 and 17. Take a look in Carleton, chapter 22. Be aware of these things because I don't know what's on the National Board Certifying Exam, but I can make an educated guess, and my money says that you will get questions on digital imaging, but to what extent, I don't know. At this point, I've gone through this section 4 on 2A and page 7. I'm going to end this video now. If you have any questions on this stuff, please reach out, write to me directly, and I'll do my best to answer it. Thanks for your attention, guys. I'm going to record one other video, as well as I look forward to a live lecture at some point in the near future. See you soon.